Students, today's lecture is on regression. First, we will study the linear and nonlinear least squares regression. I mean, mostly linear least squares regression and a very little bit of nonlinear least squares regression. And then we will extend the ideas to Bayesian regression because we want to deal with probabilistic models and probabilistic form of regression. So we will quickly switch over to Bayesian regression. But before understanding Bayesian regression, it is very important that you are thorough with the concepts of linear regression, that is the deterministic linear regression. Okay, so I will share my slides and let us start discussing about ordinary least squares regression. Now, what is ordinary least squares regression? Well, what happens really in regression? Suppose you perform some experiment. Okay, let's say you are performing some laboratory experiment involving force and velocity from wind tunnel experiment. So you have basically an independent variable which is force, and then you record the velocities, right, for different values of forces. And this is the data that you get from the wind tunnel experiment. So regression, what is to be understood at the very outset is regression is an experimental, it is an experimental technique. Unless and until we have experimental data or data obtained from numerical experiments. I mean, numerical simulations can also be, mimicked as experiments, right? So either way, if you don't have experimental data, then the whole point of discussing about regression is meaningless. Okay, so I mean, coming back to regression, let us say we have the data. So what do we now do with this data? What is the silliest or maybe the easiest question to ask is, can we form a mathematical relationship, or can we develop a mathematical relationship that connects these two these data sets, basically the relationship between force and velocity, right? So as you can see, intuitively we can fit different types of straight lines. See, if I fit this straight line, what happens is it passes through 3 points, but it misses out other 5 points. So I can also fit another straight line through another set of points. Maybe I can even fit a parabolic curve, right? So the point is, which of these curves are unique, or let's say unique in some sense, right? Or optimum in some sense. So as you can see, the choices are, the number of choices are infinite. But then the question is, which one to choose and how do we choose? So the whole idea is we choose the curve which satisfies the least square error condition, or which minimizes the least square error or the square error of the observations. Okay, so let us see how to mathematically project that statement. Okay, suppose you have this set of observations, right? Suppose you have this set of observations, and for each of these observations, let us say you assume a straight line. You assume a model, a linear model, y is equal to alpha x plus b, or let's say a straight line model that is the best representation of the data in least square sense. Okay, well, we have not talked about least squares. So let us say we assume a straight line which is the best representation in some sense, right? So pass through all the points. So for each of these points, what we can do is we can find out the error. That is, since we have the data yi and xy. So what are we given? We are given the data set which is represented by xi, yi. So for each of those points, we can calculate the errors, right? What is the least square error method, or the least squares method? Is you choose that alpha and that beta which minimizes the square error, that is square error of the observations. That is, you have the EIs, so you form EI squares for all each of these points, sum them up, and you minimize them with respect to alpha and beta. So this is basically an optimization problem, right? So you take the partial derivative of the square error, which is basically sum of the squares of errors, which is SR. You take the derivative of partial derivative of SR with respect to alpha and beta and set them to 0, right? So what does this do? It gives you basically the unknown coefficients alpha and beta. So observe, when we chose this model, y is equal to alpha x plus beta, we didn't know the values of alpha and beta. So given these observations, this is precisely what we wanted to do. We wanted to find out alpha and beta, which are the unknown coefficients, right? So this can be done by minimizing the sum of the squares of errors. Now, the question that comes is, few important or interesting questions come. The first thing is, well, leaving aside the mathematics, one of the easiest mathematical curiosities is, in order to fit a straight line, you only need 2 points. But then why did we end up fitting a straight line for so many number of points? So what sort of mathematical problem are we dealing with? We are dealing with a problem in which there are lot more number of equations than the unknowns. Your unknowns are 2, but your equations could be 100, 200, 300, right? So basically the number of data points, the number of equations. If your xi's and yi's, like pairs of xi's and yi's, if they are say 20 or 30, so you get 30 equations, but your unknowns is 2, right? So this is the first mathematical counterpoint which you need to understand, that we are dealing with an over-complex problem, and there is no no solution is possible, no mathematical solution is possible. The only solution that is possible is this least square solution. That is the first and most important observation. Now the second point is, when you estimate these coefficients alpha and beta, right? So what do we say? That by plugging in the values, the coefficients alpha and beta, we can only find out an estimate of y given x. So it is not exact. So there will always be that error, because remember, you minimized the sum of squares of errors. So your error is inherently sitting there. Although we have minimized the error, we have never said that that error is equal to 0, right? So that is the most important point. This is just an estimate. Doesn't mean that the error will be 0. The errors will still exist, right? That is very important. So this can be easily extended to 2 variable case, and for that matter, multivariable case. Okay. So please give me 10 seconds. I'll be back quickly. So coming back from the single variable to multivariable regression, that is the 2 variable case, what do we have is the same problem, but here we have, instead of y versus x, y is equal to alpha plus beta x type of problem, what do we have is y is equal to c0 plus c1 x1 plus c2 x2 type of problem. So here your unknowns are x1 and x2, and you are trying to fit a linear relationship, establish a linear relationship based on the observed data of the triplets, that is y, x1 and x2. So remember, your yi, x1i and x2i, this will be provided to you, and based on that observations you have to find out the unknown c0, c1 and c2. So again, following the same idea, that is minimizing the sum of square of residuals, right? Then I mean, by taking the partial derivatives and then setting them to 0, you can find out C0, C1 and C2 by sort of rewriting the equations in a matrix format, which is shown here. That this is a very simple way of showing this entire exercise in a matrix equation format. Ultimately, what we want is, we want to find out the values of C0, C1 and C2, and that can be easily done if you apply this matrix equation. Okay. So here is an example where, as you can see, the data sets for x1, x2 and y is provided. And how many data points do we have? We have 1, 2, 3, 4, 5, 6. 6 data points. So 6 data points from which you have to estimate, 3 unknowns, right? So what do you do is you find out all these quantities, that is sigma x1i, sigma x2i. You can easily find them out from the table. All you have to do is you have to take the summations and the summations of the products, apply them, and you get the values of C0, C1 and C0, C1 and C2, right? So your linear model, or sometimes called the multilinear model or bilinear model, is established. Now this is the general case. Equations are somewhat general case for even for nonlinear equations, right? So even if we want to establish nonlinear models, you can do pretty much the same exercise, right? Same set of equations. I will leave it to you to sort of do this derivation and find it out. Okay. So couple of things. See, as I said, that there will still be errors, because at best we are finding an estimate. We have never said that the errors will be 0. We only minimize the squares of, basically the sum of squares of errors, right? So there are a couple of quantities that are of interest to us. Of most importance, or utmost importance, is the coefficient of determination, which is given by s square xy divided by sxx syy. As you can see, this almost mimics the correlation coefficient, right? But why we don't use the word correlation coefficient? Simply because we want to apply this concept for nonlinear models as well, right? And for nonlinear models, the correlation coefficient, the linear correlation coefficient that we have understood from statistics and probability, is not defined. So that's the reason why we sometimes refrain from using the word correlation coefficient. Rather, we use coefficient of determination. These are all definitions, nothing fancy going here. And then there is a simple error analysis that you can perform for linear fit. For the linear regression model, you perform the error analysis. So you can calculate all the errors, but the most important point take away here is that the R-square that you can see is 0.869, which says that the linear model, linear regression, is a good practical approximation for this data. I will not say very good, but it is still workable, because it kind of explains only 86.9% of the uncertainty. But there are better models possible. Sometimes, by choosing a nonlinear model, you could reduce this error even like you could explain almost more than 90% uncertainty, and that would be a better model, right? Now, confidence intervals. Why is confidence interval important? See, confidence interval is important because you have to remember that the regression that we talk about, the regression model, is not what you call, like there will always be errors in the regression, right? So a regression model will always be explained with the help of the error terms. Without the error, regression does not hold any meaning. As you can see here, any linear regression model in its most general form can be written as yk is equal to theta 1 plus theta 2 tk plus epsilon k. Now, the reason I'm showing this equation, hopping a couple of slides and trying to show you, is the regression is not exact. We never said that we made the errors zero. The errors are always present. Now, what is that most important characteristic of the error? The most important characteristic of the error for linear regression to be valid is the error is a random variable. The error is a Gaussian random variable with zero mean and some standard deviation or some variance, some standard deviation sigma or some variance sigma square. Now that is the mathematical statement of linear regression. So it is yk is equal to theta 1 plus theta 2 tk plus epsilon k, or you can say that yk is equal to alpha plus beta xk plus epsilon k, right? So one of the most important characteristics of the linear regression model is the presence of this error term, which is assumed to be of zero mean and some constant standard deviation. That is a normal random variable of zero mean and constant standard deviation, which is sometimes called the homoscedastic model. The standard deviation is constant, but the error is a random variable. So as you can see, since this error is a random variable, it is possible to form what we call as maximum likelihood model for linear regression, which is something that I can ask you. Okay, I mean, I will ask. I'll let you think about it. That how you can formulate the maximum likelihood model for linear regression. But I'll show you how to do the Bayesian one. So the simplest one is the linear regression using least squares. The most complicated one is the Bayesian regression, the Bayesian way of looking at regression, and somewhat intermediate or intermediary idea will be the maximum likelihood regression. Okay, but I will not do that, and I'll leave it as an exercise to you. I'll remember this because these are video lectures, and you cannot say after a point in time that sir never told. I am actually telling you, okay, letting the cat out of the bag. That is, please figure it out yourself how to do it. It's an exercise, as simple as that. Now, confidence intervals. Now, why is confidence intervals necessary? The confidence intervals is necessary. The confidence interval is necessary because of the presence of error term. As you can see, because of the presence of the error term, you can always say that the alphas and the betas that you find, they will have a bound. They will have an uncertainty bound because of the presence of that random variable, which is in the form of the error, right? Because if the error is the random variable, every time you run the model, let's say you have created the model, let's say you have a regression model with an error term. Every time you run the model, let's say you simulate the model, the random sampling of white noise, every time, even if your alphas and betas are constant, every time you are going to get different sets of values of y for the same x, just because you have that error term, that random variable sitting over there. That random variable messes up everything. And this mess up, I mean, is what we sometimes call as the sampling uncertainty. I have mentioned this or discussed about this IID sampling and sampling uncertainty in many different ways, right? While talking about this, what we call as this maximum likelihood method, this IID sampling was discussed, right? Independent and identically distributed sampling, right? So let us see, how do we talk about confidence intervals? Let X be a random variable whose population mean is unknown, right? So population mean, what is population mean? It is basically the integral x px dx minus infinity to infinity. That quantity, that theoretical quantity is called the population mean. Let's say, let us also assume that the variance is known. Well, sometimes these assumptions have to be made in order to explain you certain things, okay? Because if both mean and variance are unknown, then this whole mathematical treatment becomes a little difficult. So what we'll do is, let us say let X be a random variable whose population mean is unknown mu. So if we sample, if we perform IID sampling, well, let us say we perform random sampling. Now, random sampling means, that is, we sample n values, that n can be very large, okay, n values from the random variable. Let's say we are making n observations. So the first set of observations of x1 to xn will be x1 of 1, x2 of 1, x3 of 1, x4 of 1, and xn of 1. It means it is the first sampling that you have done, the first set of n values. So the sample mean will be mu x1. Set of observations can be, similarly can be labeled as x2, x1, 2, x2 of 2, x3 of 2, and it goes until xn of 2. And the sample mean will be mu x2. Now, ideally mu x1 should be equal to mu x2, should be equal to mu. But then, what is the sense of that ideality? What does it mean by being ideal? Meaning that number of samples should be infinite, right? Now, you are not going to get infinite number of samples in real life, can you? It is not possible. Why is it not possible? Because of obvious limitations of performing a random experiment. So you cannot perform infinite number of experiments, and I have talked about this many times. So this paradigm should be easily understood. Say if you are doing a concrete testing, in a concrete compressive strength, strength testing, you cannot perform infinite number of tests, and that is not possible, right? So similarly, you can get first set, second set, third set, n sets of n observations. So the question is, how good is mu xi an estimate of the mean mu? Well, I have made a small mistake here. The mistake is, this mu is not the sample mean. It is basically the population mean, and mu xi is the sample mean. So how good is the sample mean, which is mu xi, an estimate of the population mean? So please mark the typographical error here. So that is point number one. I mean, that's the question we are asking. So mu x, what you understand, what is very easily understood is that this mu x1, mu x2, these are not going to be constant. They are going to fluctuate. So it means what? Because of random sampling, your mean is also becoming a random variable. Because mean is not constant, the sample mean is not constant anymore. Depending upon the number of samples you make, depending upon the size of n, depending upon how many set of observations you make, your mean value is going to fluctuate. And you can see this. You can perform this random experiment yourself. It should be fairly easy. All you need to do is just open MATLAB. Just use that rand n 1 comma let's say 500, meaning you sample 500 random values from Gaussian distribution with 0 mean and 1 sigma. Okay, so what do you do is, Once you have sampled them, find out just by using the MATLAB command the mean and the STDV, that is average and the standard deviation. And you keep doing that, repeating that exercise as many times as you want, 50 times maybe. So what are you going to see? You are going to see 50 different sets of values of mu. So it means what? Because of this effect of random sampling, your mean is also a random variable. So in that case, since x1, x2, x11, this can be considered as IID observations of the random variables x1, x2. That is, we make this, this is the trick. This is an IID trick. It is called independent and identically distributed. Right. So we are saying that x11, x21, x31, x41. They are basically IID observations of the random variable x1. So it means your every sample x1, small x1, it belongs to the random variable capital X1, right? And every sample small x2, it belongs to the random variable capital X2. Now this is the II part, the I part, that is the independent part. Sorry, this is the I part, right? The second ID part is identically distributed, meaning since we are talking about one random variable, that is the mother random variable is x, all these x1s, x2s, x3, capital X1, capital X2, capital X3, capital X4, they will have the same distribution, the very same assumption that we made for maximum likelihood method, right? Although these are sample observations, so it can be assumed that a sample is a fairly fairly decent representation of the population, and that each sample observation is independent of another sample observation, and each sample observation is identically distributed to another sample observation. So let us take the sample mean and let us see what is the randomness of the sample mean. So what do? Is we find out Ex, expected value of the sample mean, and the variance of the sample mean, which comes out to be the expected value of sample mean. If you just apply the expectation operator, you see that it comes out to be mu. So that expected value of sample mean is equal to the population mean. Now, so this is one of the profound results coming from random sampling theory. So even if your sampling is random, it can be proved that the expected value of the sample mean, which we assumed as a random variable, that expected value of sample mean is exactly equal to the population mean, right? And the variance of sample mean, we said that the sample mean is a random variable, right? It is understood. So if sample mean is a random variable, one can find out the statistical descriptors of sample mean, basically the expected value of sample mean and the variance of the sample mean. So it sort of turns out to be mu and sigma square by n. Now with this background in mind, sometimes what question do we ask is, for mean mu with known variance, can we find out the confidence interval? Now what is confidence interval? So basically we have said that the mean is a random variable. So if we assume that the mean is a random variable, that is the sample mean is a random variable, is basically normally distributed with mean mu and standard deviation sigma y square root of n, or variance sigma square by n. So what we can do is we can find out confidence intervals. Now this is exactly the definition of the confidence interval. So what is the definition? Definition of confidence interval is basically 100 into 1 minus alpha in terms of percent. Okay, 100 into 1 minus, let us forget 100 into 1 minus alpha percent. just say 1 minus alpha. Your 1 minus alpha is the confidence interval, and if 1 minus alpha is the confidence interval, as you can see, the quantiles are expressed by alpha by 2 and alpha by 2 on both the sides, and the corresponding values on uh, the data axis is k alpha by 2 and minus k alpha by 2, right? So assuming, as I said, assuming that the sample mean is normally distributed with parameters mu and sigma by square root of n, we do the standard normal transformation. That is, we subtract the mean and basically x minus mu by sigma, that is standard normal transformation. The definition of confidence interval is the probability that x minus mu, x bar minus mu over sigma by square root of n, it lies between minus k alpha by 2 and k alpha by 2. That is given by 1 minus alpha, right? Which is called the confidence interval. Therefore, the confidence interval around mean is given by x minus k alpha by 2 into sigma by square root of n, and x bar minus k alpha by 2 into sigma by square root of n, and x bar plus k alpha by 2 into sigma by square root of n. Now, what are these values, k alpha by 2 and minus k alpha? These are quantile values, right? So if you want to choose a confidence interval, you are talking about values, right? You are talking about the values within which the mean is expected to lie, the sample mean is expected to lie, right? Or basically the confidence interval, sorry, not the sample mean, the population mean is expected to lie, right? Again, sorry, not population mean, the sample mean. Let's say the values within which the mean is expected to lie, right? That is the confidence interval. So let us take an example. Sometimes even I mess up with these definitions, but one example will easily fix the ideas. Let us consider 41 observations of Young's modulus in the table. The sample mean and standard deviation are given. These are some values in KSI, and pardon me for the units. This is an example taken from Haldar and Mahadevan's book. You can go through it, right? It is taken from Haldar and Mahadevan's book, right? So assuming that Young's modulus is known to have a population standard deviation of 1507 KSI, determine the 95% confidence interval for the mean and 99% confidence interval for the mean, right? So as you can see, the sample mean and sample standard deviations, these are provided, right? The sample mean and standard deviation. And the population standard deviation is also known. So what do we want to find out? We want to find out basically the bound 29,576 plus delta and comma 29,576 minus delta. That is the interval, right? So 29,576 plus delta, sorry, minus delta, and 29,576 plus delta, right? Such that there is a 95% confidence, and then there is 99% confidence. So what do we have is, we now so from here, so this is the data that is being provided, right? So now what I will do is, I will so I will take that example. As you can see, these values, these are taken from Haldar and Mahadevan's book. So based on these values, so what we do is, we want to find out 95% confidence interval. Okay, 95% confidence interval. So 95% confidence interval means 1 minus alpha is equal to 0.95, right? and alpha is equal to 1 minus 0.95, which is 0.05. Just give me a few seconds. I'll be back. So 1 minus alpha is 0.95. So alpha is equal to 1 minus 0.95, which is equal to 0.05. So your alpha by 2 is 0.025 and 1 minus alpha by 2 is 0.975. So how do you find out the k alpha by 2? K alpha by 2 is k of 0.025, right? K alpha by 2 is 0.025. So you find out k alpha by 2. These are the quantiles, right? So you can find out using the standard normal tables, right? So k alpha by 2 is equal to k 0.025, which is equal to phi inverse of 0.975, which is 1.96. The step 3 is applying the formula, that is sigma by square root of n. Sigma is known, that is the population standard deviation. And you have found out basically the deltas. So the 95% confidence interval is given by this, right? 29,576 minus 461 colon or comma 29,576 plus 461. Okay, so this is the confidence interval, 95% confidence interval. You can take a guess that if it is 99% confidence interval, it will be a smaller or wider interval. It will be a wider interval. Okay, it will be a wider interval. What I will now do is I will stop sharing here, and I will again start sharing, stop sharing and stop video recording, and start sharing and start the video recording again, just to make sure that this entire video recording is happening perfectly. Okay, because I don't want to take a chance because of this, stupid internet connections that we have these days. Okay, so I will stop sharing, stop the video recording, and again start the video recording. Okay,